In this video, we're going to learn a new relationship, which will be very helpful for us using calculus to solve these kinematic problems. And then we're also going to just really quickly derive the rest of our constant acceleration equations using calculus. So this is yet another video on calculus. We'll start off with two expressions that we're familiar with. So we know that v equals the change in position. I'll just say s instead of x because it can be in the x direction or the y direction, divided by the change in time equals ds if you're using calculus, and that gets us much more precise. And we also know that acceleration equals the change in velocity divided by the change in time equals this using calculus. Now we want to derive we want to get a relationship between acceleration and velocity that doesn't involve time, because sometimes in problems we're not given time and we don't need to solve for time. We just want to relate acceleration and velocity. They'll say at this position the velocity is this, and the acceleration function is this. Find the velocity at this other position. Time has no role there, or it doesn't have to have a role there, and so we want to be able to relate velocity and acceleration. So what we're going to do is we're just going to say, okay, if I multiply change in time, so I'll solve for the change in time. Change in time using the second equation equals change in v divided by acceleration, just doing a little bit of rearranging, and then I'm going to plug this change in t back into this change in t. So what does that give me? That gives me v equals change in s divided by change in t, which is change in v over acceleration. Well, that looks a little messy. I will get this v divided by change in delta v divided by acceleration onto the other side. So velocity time equals delta v divided by a. Just verifying that I've got all this correct. So I'm going to multiply. What am I going to multiply both sides by? Let me just switch colors so that this is clear. I'm going to multiply both sides by this. So I'm going to multiply by, I'm sorry, I'm going to divide both sides by this, and then I'm going to divide this by acceleration divided by change in v. What'll that give me? That'll give me velocity times change in v over acceleration equals change in s. And then rearranging that again, I'll get v change in v equals a change in s, and these are all actually vectors. But now what where we want to go with this is we want to use infinitesimally small pieces and then say that, okay, v dv equals a ds, because now this gives us a whole. Before we said, all right, acceleration equals dv over dt. Nice, we've related acceleration and velocity, but it's with time, not with respect to displacement. Now we've got acceleration and time related through this ds over dv. And does this make sense? Well, let's just look at that. So it says that this claims that a equals v times dv divided by ds. What's velocity? Velocity is just ds over dt, and then that we're multiplying that by dv over ds. If we look at that, this cancels out, that cancels out. We're really just saying a equals dv over dt. If you look at, from a fraction point of view, this is legit. dv over dt is legit, but because we say ds over t, which is velocity, times dv over ds, now the t is hidden in there and we don't actually need to be given information about t. So let's use this information to derive our one of our stranger looking constant acceleration equations. And so let's just write this expression out. v dv equals a ds. What would happen if we took the integral of this, starting with velocity initial, all the way to velocity final, and we took the integral of this, now this is with respect to s, ds, so from s initial to s final. One thing you'll notice is we can do indefinite or definite integrals. If we do indefinite, we have to add a constant in. If we do definite, we don't need to worry about that constant. You'll see that as we go through these. But for here, I'm doing a definite integral, so we go from velocity initial to velocity final, from position initial to position final. Well, the integral of v dv is just v squared over 2, evaluated at vf and velocity initial, and then equals, now acceleration is just some number like 9.8 downwards. So we can actually move the a outside of here and it just becomes the integral of ds, so equals a times s. The integral of ds is s, evaluated at s final and s initial. Well, plugging values in, what do we get? We get vf squared minus v initial squared over 2 equals a times sf minus s initial. Velocity, now where do we see this? We saw this equation in a slightly different format, but it's velocity final squared minus velocity initial squared equals 2 times the acceleration times the displacement, change in s, s final minus s initial. So this was one of our constant acceleration equations, and we can get that just by calculus. One thing you'll find is that you actually don't have to memorize the constant equations. You can derive them. What you need to have memorized, I'll write up here I'll write here in red. So the key relationships that you really have to know. And I'm running out of room here. But the key relationships are ds over dt equals v, and dv over dt. So the change in displacement is velocity, which, I mean, that's almost the definition of velocity. And then the change in velocity with respect to time equals the acceleration. And then you don't really have to, I guess you can derive this one from these two, but it's helpful to remember that velocity times dv equals acceleration times ds. So this one isn't quite as fundamental as the others because it can be derived from them, but if you remember these three relationships, you can derive your constant acceleration equations from those. So let's derive the last few minutes, let's derive our final, the one equation we haven't derived yet, using calculus. And for that, let's just look at the definition of acceleration. I'm sorry, let's look at the definition of acceleration. So acceleration equals dv over dt. Okay, so that means we can multiply both sides by dt. A dt equals dv. And now let's take again we'll do the definite integral so we don't have to worry about constants. Starting from, so dt with respect to time, from time equals 0 to time equals t. So from 0 to t, and then dv, so the integral with respect to v, from velocity equals some initial velocity all the way to velocity equals velocity final. So remember, whatever the d blank is, it can be a little confusing. You might think, all right, from a initial to a final. No, just from with respect to time, so from time initial to time final. With respect to velocity, velocity initial to velocity final. The integral of a with respect to t, if a is a constant like 9.8, we can move that out. It's just a, and then dt, integral of that is t, from 0 to t, equals the integral of dv with respect to v is just v, evaluated at velocity final, minus velocity initial. Well, that just gives us a t minus 0, which we won't include, equals velocity final minus velocity initial, or velocity final equals velocity initial plus a times t. So in the previous video we derived one of the expressions. Here we've derived the two other constant acceleration expressions, taking definite integrals and just using the basic relationships that velocity is the change in displacement over the change in time, or the derivative of the displacement function with respect to time, and acceleration is the derivative of the velocity function with respect to time.